Yes. Okay, so it's 11:01. It is a good time to start. So welcome everyone to our keynote session, our second keynote session of the conference. And I'm delighted to introduce the speaker. So Professor Fabio, he's a full professor in the Department of Computer Science at University of São Paulo in Brazil. Fabio's research interests are very broad. He has worked with distributed systems, scalable systems, software engineering. He had a very important role in the open source movement in Brazil and South America. He works with a lot of people in multidisciplinary projects in data science. And more recently, he has put a lot of his energy on smart cities, and that's the part of the work he's going to talk to us about today. He's also involved in evidence-based public policy making, which sounds like something that all of us need to be doing in one way or the other, and DevOps. Fabio is an ACM distinguished artist. I read on his bio that he wishes he had more time to play the vibraphone. So I had to Google to see which instrument. I know Fabio has been dedicated to music and also other things like literature across his career as computer science, but the vibraphone was new to me. What else I wanna say? I would also like to say that professors like Fabio in South America had an important role in getting system software to be respected. We had a tradition in the country that was very focused on theoretical computer science, lovely, wonderful work. But I think Fabio and his generation really got the systems research in Brazil in the map. Let me do a plug-in. If you want to learn more about Fabio work and other people in South America, they're in the communications of ACM of this month. There is a special session on research in Latin America, and I found the articles very good. So I recommend you consider taking a look. So Fabio, that's up to you now. I'll be monitoring both the Zoom chat and the Slack channels. I will see if we have like multiple questions in a theme, I may interrupt you. Otherwise, we will have the questions in the end. Thank you.
Okay. Thank you very much, Dilma. For me, it's a great pleasure to be giving this keynote since the Middleware conference is a conference that's close to my heart since the first edition in '98. So I was very glad when I received the invitation from the PC's chair. So thank you very much. So as Dilma said, in the past 5 years, I have been working in the field of smart cities. And I'll tell you now a little bit about what we have been doing in terms of developing and assessing middleware and applications for smart cities. But first, let's talk about what is a smart city, because our view is may be a bit different from what we see in some places in the literature and also in commercial flyers from companies. Okay, so first, for us, a smart city is not a city with lots of technology, autonomous vehicles, 5G networks everywhere, and cameras spying on us. A smart city is a city in which the citizens are happy, healthy people. You probably have very few cars and lots of pedestrians and bicycles, people going to work by bicycle, going through green areas, parks, in healthy and pleasant environments. And the citizens of the city have an active role in the governance of the city. So this is our dream of a smart city. And the really good news is that there's a lot of work that computer science can do to help achieve that dream. So data science can be used so we get insights from the huge amount of data that the cities are starting to generate and get information and insights to help the planning and designing public policies for the cities. There is a lot of work that in software engineering and human-computer interaction that we can do to develop innovative applications that the citizens of the city would use to interact with the services of the city. And there's a lot of challenges in software system design and implementation to make this strange new thing work. And of course, a lot of middleware work. We have been working in the past years in all these items here. In particular, we created a group, a research group called Intercity, in which we put together 35 computer science professors from different universities in Brazil to work together with professors and researchers from other fields, in particular from architecture, urban planning, economy, health, and transportation. We also have partnerships with city governments and government agencies because our idea is to create the science and technology and transfer the knowledge to real cities. So these partnerships are important not only to transfer, but also to get the requirements and better understand the problems of these cities. So basically the goal of the project is to use science and technology to support urban public policies. And our focus on smart cities is not on creating high-tech cities from scratch, like the cartoon Jetsons, something like that. No, we are focusing on most of the cities, most of the large cities in the world where 90% of the people of the planet live, which is a city like this one in the picture. So remember that 90% of the world population is low-income people, mostly from developing countries, and they live in underprivileged neighborhoods, and there are many important social problems that need to be addressed. So 90%, this by chance, this is a picture from the city where I live, São Paulo, and 90% of the world population of the human beings live in a place like the one in the downside of this picture. We scientists and the other lucky 10% live here, up here. So our focus is improving the life of these kind of people. And we have been working in different fields. So for example, in healthcare, providing innovative dashboards for policy making in the area of health. Also in accessibility, we have been working with the São Paulo Secretariat of People for Disabilities, to collect data from different sources and make a map of accessibility problems in the city. Alumni from our research group, students that graduated, created a startup company that now manages the São Paulo public transportation system based on buses. So there are 15,000 buses that are in real-time tracked, and they developed this real-time dashboard that provides lots of insights, both in real-time for the system operator to better improve the system that transports 6 million people every day, and also for long-term planning. And we also have done, for example, data science work in which we collect data, mobility data from non-motorized modes of transportation, for example, bicycles and pedestrian movements, and try to understand what the major, most important mobility flows of the population in the city, and use this information. For example, this is the cycling flow of people in Boston. Use this information to provide evidence for public policy making. In São Paulo, the city government is now using this tool to plan the investments in the cycling infrastructure in the city that will be invested in the next 2 years. Okay, but we also have a lot of, in this field, a lot of middleware work to do. And that's what I'm going to tell more about today. When we started this project 5 years ago, we started to visit different city governments and secretariats from different sectors of the city, health, transportation, education. And what we found was that they already had IT systems, but these IT systems, they were vertical silos that were completely isolated from each other. So you couldn't do any combined analysis from data, for example, from mobility and education or health and education. It was almost impossible. And besides that, each secretariat would reinvent the wheel. So all the implementation stack here, it was duplicated, triplicated in slightly different ways, but all of them doing the same thing, duplicating the effort. So as middleware researchers, we had a dream. The dream was, what if we had a single middleware layer here, a smart city platform that would receive data from different IoT devices, sensors and actuators in the city, and also data from other systems, other sources. And this middleware will contain all the basic elements that are needed to develop this kind of application. And then on top of that, much more easily, you would develop the specific domain applications. And not only it would be easier, but also you could have a management system that could use data from different sources to make a cross analysis. So before doing that, we started by studying 23 smart city initiatives around the world to understand the software they had developed. And from that, we collected the requirements and the challenges for such a software platform. And this became a paper in the ACM computing service where we propose a reference architecture for smart city software platforms. And then we started to implement an open source version of at least a part of this architecture based on elastic microservices. And this is what we call the intercity platform. What the platform does is to manage heterogeneous city resources, integrating different IoT systems. It provides support for data storage and data processing, and also context-aware resource discovery based on the geographical location of the resources within a city. Also, on top of that, the platform provides a REST API in which we can use to develop web applications, mobile applications, and eventually development tools that would interact with this platform. The idea is that IoT devices and other data sources will register their resources with the platform and then post the data they generate from different sources to the platform. Also, some of these devices can subscribe to receive actuation commands. For example, a traffic light could receive actuation commands from the platform. Then on top of this platform, we started to think about what applications we could have. And a nice thing we did was to use this as an educational tool. So we started using this in courses in the University of São Paulo and later in other universities. They are mostly smart city development courses in which the students during a semester, they come up with a proposal of a smart city application. They need to find the data and the tools, and then they create the application on top of the platform. The students really love this experience because they feel they are building something more real that can have an impact in daily life, and they learn a lot about middleware and open source tools and software, agile software development. So the students love it, and they develop some interesting applications. For example, one group developed this smart parking app, which was a cell phone app in which you configure it to tell what are your preferences with regard to parking spots. And then before you leave to your destination, for example, if you go to a theater or before going to work, you tell where you are going. And when you are reaching the destination, the software accesses a database of available parking spots at that moment, reserves one for you, and directs the route so you can drive up to the destination. Another application that I like a little more is this outdoor sports map. What the students did, they collected data, in real time for different aspects in the city of São Paulo, like air pollution, humidity, temperature, UV index. And they also incorporated in their application a map of the green areas of the city and also of the bicycle paths. And then the application real-time draws this heat map, telling you what are the good areas for you to practice some sport, like to go jogging, for example. So it's showing this area here, for example, is in green. Green is good. So you have cycling tracks there, and you have a place for jogging, and the area is green, so it's good right now. This area now is red, is bad, so you shouldn't go there now to practice sports. So it's very nice that the applications work. It's a great tool for education. But this year we had another experience that was more real. In the beginning of the year, the government of São Paulo, the state of São Paulo, decided that they wanted a situation room for the COVID-19 crisis, and then they called IPT. IPT is a technological research institute in the state of São Paulo that they are supposed to develop technological solutions for the state. And so the governor asked the IPT to develop something for this situation room. And then IPT, the good thing for us, they decided to use the intercity as part of the middleware that they were using, and they put up this is a real picture from the situation room in the governor office. And what they do here, they get lots of information from different sources. For example, there are traffic counters and speed trap cameras and automatic vehicle identification spread throughout the state of São Paulo. The state of São Paulo is a large area that has 40 million people. It's a larger population than most of the European countries, for example. And so these sensors are spread throughout the state, and they belong to different companies or different government agencies. But they all produce data. And up to now, this data was not concentrated in a single location. And also, they collected data from smartphones, from city officials, and point of sale hardware to track the business activity in the state, and also got information from public health system to track the evolution of the pandemic in the state of São Paulo. So all these different sources were sent to a central location and then visualized. So this is an example of different kinds of visualization that are done. This is an IPT researcher and a City of São Paulo employee discussing about the data, and this was actually used as evidence-based support for the policies that the São Paulo state used to tackle the COVID problem this year. And it was very good that they did this using a scientific basics, because other parts of Brazil didn't do, and it was, as you might have read, really bad. Here we have the largest population, but the situation was relatively under control because science was used. So, okay, so it was nice to see a third party using our middleware to develop something useful to society, but we have our middleware challenge, which is how to assure that the middleware has a good performance. How is it capable of handling real workloads? Because we were using it with these toy applications that the students were developing, and these applications had like 5, at most 10 users, which were the students themselves. And even this COVID-19 application is actually only collecting data from about 20 different sources, combining the data and visualizing it in nice ways. But it's not a huge scale. But when we talk about the smart cities of the future, we talk about having thousands or probably millions of sensors and actuators and thousands and millions of users. And we didn't test anything even close to that. So how can we test the performance in these real environments? It's too expensive for us. We don't have access to a system with millions of users and millions of sensors and actuators. Maybe Google has, but any other researcher in the world probably doesn't. So normally, as researchers, what we do, we tend to write scripts that would represent synthetic benchmarks, and we do that, but how realistic the workload that we are generating is. So this was a question we had. So to evaluate the performance and the scalability, real scalability of this middleware, to see if it has a chance of working in a city like Sao Paulo, what we did was we ran 2 main rounds of experiments. Each round had several improvement cycles to the middleware. It was not an assessment, it was an assessment paired with refinement of the middleware itself and a scalability assessment. So the first round was based on synthetic workloads, in which we had hundreds of simulated IoT devices continuously sending data to the platform. And then the second round, we did a really large-scale workload using simulation. So I'll tell you a little bit about that. Our idea, and this is a diagram that was in the thesis of one of my students. He drew the diagram, but now I show it to all the new students that come to develop systems with us. Because the students think that they developed the system, they tested it in their computer, and okay, the system is ready to ship. And say, no, it's never like that. If you test it with one user, you need to test. If you test it with 10, it will break. Then they test with 10 and fix, and I say, okay, now if you test with 100, it will break. And then they do, and then it breaks. Then I say, okay, now if you test with 100,000, it will break again, and it breaks again. So the process that we are following is this. We come up with an initial version of our middleware, and then we perform some lightweight experiments to identify the bottlenecks. And by lightweight, I mean an experiment that can run in a few minutes or at most a couple of hours. And normally when you are starting, you will quickly identify bottlenecks by looking at the resource consumption of each of the components, and also looking at the response time that the components have. And then you come back to improve your design. Maybe breaking a microservice in 2 smaller microservices, adding some replication, elasticity, tuning the parameters, using different algorithms, different databases, different indexing policies. And then you keep cycling here until you reach a decent quality of service that you believe it's good. And this is a way of refining and assessing the middleware at the same time. And then when you believe you are ready, then you go to a more comprehensive experiment with a scalability analysis. So the way we did that was first, the student said that, okay, the system is ready. And I said, okay, so just run one synthetic benchmark, just send the requests as fast as possible, and what happens to the system. Then quickly identify that there were 2 bottlenecks, the resource adapter and the data collector, and the performance of that version of the system. It was fulfilling a complete request exercise, exercising all the components of the middleware in 4 to 5 seconds. And I said, okay, but 4 to 5 seconds is too much for an interactive app. People will complain nowadays. So let's set the QS goal. I want the fulfillment of the user request on average less than 2 seconds. And I want in 95% of the requests less than 4 seconds. And I want this to hold for 500 users. So, okay, so the student went back to the lab to try to optimize these components and to experiment, to help in evaluating that. What we did, we set up a system in which we had the FuncLoad tool generating increasing loads, simulating increasing number of IoT devices, posting data to a part of the platform. And we put we were looking at the 2 components that were the bottlenecks, initially with no replication. And then they find a lot of small problems in the code, or different parameters that they needed to use, or they changed the underlying middleware that they were using for communication. And then progressively over 2 months, they were able to make these optimizations and improvements. First, made the response time under 3 seconds. And then after a while, with 500 users, they managed to make the response time 1.2 seconds, and in 95% of the cases under 4 seconds, reaching our QS goal. Okay, so said, okay, you reached the QS goal, so let's do a scalability analysis to see if the system is scaling well as we put more resources into the system. And the way we tested this is by having a fixed number of clients, 500 clients, and we increase the rate in which these clients send data to the platform. And now the platform has enabled replication, and as the load increases, we let the elasticity mechanism to increase the resource. And then what we wanted to see actually happened. This was a good surprise. The scalability was pretty good and linear. As we increased the number of resources available to the system, so the number of requests per second that the system could fulfill, keeping that quality of service, increased gracefully in almost completely linear. So with 6 replicas, we could have a speed up of 5.39. I said, okay. So we used this design approach to achieve scalability, like functional decomposition in microservices, and different technologies and different design approaches for each of the microservices based on what they do, different communication styles in different places. Part of the systems is asynchronous, part is synchronous. We have an independent deployment with independent scalability of the microservices, and so we reached that good level of scalability. Scalability is good, the code is available and works, but this workload is very far from being realistic. We say in our motivation that we want a platform that can handle real workloads from a city like São Paulo, 12 million people using the system. And we are not even close to that. And we don't have real traces. A nice thing that I learned from Martin Van Steen is that trace-driven simulation is a nice thing. We wanted to do that, but we couldn't because we didn't have any real traces and no similar system generating this kind of load in a city such as São Paulo with 12 million users. So how can we test that? But then we had an idea. We had in our project this PhD student that was finishing. He was completing this intersimulator. It's an Erlang-based simulator that is capable of going very large scale, simulating large things. You can simulate a neighborhood in a city, or you can simulate a full city like São Paulo with all its streets and each citizen of the city. So for example, we ran simulations with 17 million people moving around the city, and we have specific agents to mimic the behavior of cars, pedestrians, buses, subway, and bicycles. And we had been using this to analyze the impact of changes in the transportation infrastructure in the city and the associated costs. So for example, if you build a new subway line, what happens in terms of cost, carbon footprint, the traffic, and so on. So we were doing that. And we had the idea, why don't we use this simulator to generate a simulation of the city? And then this simulation of the city will send real requests. Then they are not simulated anymore. They are real REST requests to our middleware, and the middleware would be actually running, not simulated, running in the cloud. So we have this system with the simulated city generating the workload for the real system and see if the system can handle it. So what we did was to have simulating car drivers using the smart parking app that I mentioned before. And we simulated the behavior of drivers using the app and the behavior of the IT devices installed in the parking spots. And we used real data from the city to simulate 500,000 cars within this time frame, their behavior. So we got real city data, the real map from the city with around 50,000 streets. We collected data from different sources to create a database of 500,000 parking spot locations in the city. And then by looking at a data set of 12 million city trajectories that we had, we found that 500,000 of these people would be people that would be using cars around this time to go to work or to go to to study in the university or something like that, and park their cars. So we actually ran the simulation. It made these 500,000 requests at a certain time from a certain geographical location to the platform. And then we plugged this simulation in the middleware that was performing very well, and it was a disaster. Because with this realistic workload, the performance was really bad. It was a performance larger than we had tested, a workload larger, and the pattern was really different from the syntactic benchmark that we had. In the worst case here, the application was taking almost 3 minutes to respond, and we wanted a couple of seconds. So I said, okay, we must go back to that cycle and improve the middleware again, look at where are the bottlenecks. And then we found that the MongoDB was a big bottleneck immediately. And so we went to study in detail the documentation of MongoDB, how we can improve it. And then we learned that if we did a smarter index in the MongoDB database, the performance would be much better. And indeed, we got a worst case of 5 seconds here. Then I said, okay, but 5 seconds is too much. What else can we do? And then after a while, we realized that we could have an in-memory database. There was no need to have it on the disk. We just needed a machine with a lot of memory, and putting with in-memory database, we made the response time to 3 seconds. But I said, okay, 3 seconds is not yet enough. What else can we do? And after a while, we realized that removing some serialization overhead that we had in the system, we could make the worst case go under 1 second. And that was, then we were very happy, because we started with this very bad situation of over 100 seconds. And in the end, in the worst case, we had on average 1 second of response time, and in the worst case, like 1.6, 1.7, under 2 seconds in the worst case in the rush hour. And then we finally said, okay, now we believe we have reached a good scalability that maybe it will handle the workload of a real city with 500,000 people using the system. It's interesting to see how all the elasticity, independent elasticity for the microservices we have, how it works differently from each of the microservices here. But a great thing that I like about research is the possibility of working with other partners, other research groups, and we love doing that. So there are some very good researchers that are using our middleware to extend it and to apply it in other ways that we didn't imagine before. So first, some people from the Federal University of Goiás in Brazil and Lancaster University, Roberto, Fabio, Ilwes, and Barry, they are applying to our middleware this idea of emergent microservices. And the idea is that the current version of the platform, it only looks at the changes in the workload volume and then see what microservice it should replicate, and then uses technologies like Kubernetes, Docker on the cloud to replicate the microservices that are more needed at that time. But imagine that you have instead radical changes in the workload pattern while you are executing. Then maybe what you should do is not simply replicating a microservice. Maybe you need to change the way that the microservice is implemented, or change the approach that the one microservice is using at that time. So they come up with this idea of emergent microservice. This is an emergent microservice in which they have a component component-based model of the internal working of the microservice. What are the internal components and algorithms and policies it uses, and with potential alternatives. And then they use a reinforcement learning algorithm to once in a while test different configurations for this internal representation. So they use this idea of reflection for having an internal representation of the microservice and reifying it and reflecting on it and changing the behavior. And then by doing that, to test that, they got the intercity platform, and they got one of the components that we had implemented, that they re-implemented it in a component-based language that they developed in collaboration with Lancaster. And what they did was to add the possibility of changing the internal workings of that microservice to incorporate cache, compression, and cache plus compression. And then put the system to work. And what the yellow line here shows, this learner microservice. It's a microservice that it has a phase of learning and exploration in which it tests different configurations, and then it has a very bad performance there. But then it finds the best possible configuration for that particular workload. When you change the workload again, it will have for a certain period a bad performance, or not very bad, but not the optimal performance when it's learning and exploration, the new workload, but then it converges again to the best possible configuration. So the idea is that they are experimenting with a combination of this idea with the elasticity that we had before to produce more robust and more efficient adaptive distributed systems. And so these are ongoing work. Hopefully, maybe they will have a paper in Middleware 2021 about this. Another group that's also working with the middleware is from Rio, the PUC Rio University, Professor Marco Zendler, together with Professor Silva from UFMA University. And they are extending the platform for what they call the Internet of Mobile Things. And the idea here is, under the intercity platform, to add a new middleware layer called ContextNet that deals with context in the fog computing, and also a mobile hub middleware that deals with edge processing and local area communication protocols. And then they are looking at and implementing, not only looking, but developing applications that are highly geolocation based. So for example, a public safety application, REAL, in which law enforcement agents and the citizen and managers use different cell phone apps to deal with public safety, or another application in which they use drones to collect data and images and other kinds of data from vacant land and urban forests, and also playing with the idea of partitioning the middleware platform in different areas based on geographical domains and the applications that are being used in those domains. So this is also ongoing work that's producing very interesting results. So that's what I like the most, to work with other researchers from outside of our research group. So to conclude the talk, I hope I convinced you that smart cities is a fascinating domain, and that computer science can directly impact the life of citizens. And there's a lot of good research to do into that direction. And we can work with mobility, health, safety, leisure, sustainability. There are lots of different aspects of a city that we can contribute, and we can contribute to the life of low-income populations in developing countries. A lot of work is needed in scalable system design, research in scalability assessment, and in particular, I want to research more this idea of simulation-based realistic workloads. And there's a lot of space for intelligent strategies for middleware adaptation. So thank you for your attention. This is what I had to say. This is the website of our project, intercity.org with SC, if you want to see the papers and the source code and other stuff. And if you have any other issue, I'm open to questions now, but feel free to email me later if that's the case.
Thank you, Fabio. Thank you very much. So people, if you want to raise your hand and ask your question, it will be better than if I read. So, I think we have time to do that. Anyone who wants to just unmute themselves, feel free. And as people think of questions, I have a bunch of them, Fabio, but I'm afraid that they are all kind of hard, because when you try to solve real problems, right, you don't solve everything. So, the two things that
I prefer easy questions, but I can try the hard ones too.
They're not fun. So two things that came, two ideas that kept coming to my mind as you spoke is, on the theme of participatory government. Did you, or do you have plans to include in the innovation team people who come up with the ideas of the technology that we want to do based on the sensors? I'm talking about the applications. Did you involve people who, let's say, live very differently from you and other researchers? I'm Brazilian like you. I'm from Sao Paulo, and I'm very aware that we have inequality across the world, but the inequality in Brazil is particularly painful, with education that is particularly sad. So how do you develop technology that will make sure that it's not technology for people, I'll say, who live like you or who live like me when I visit Sao Paulo? So this is one thing. Right. Another thing is that I'm so excited that you are so connected with the government. People really use intercity software. But then, besides performance, resilience, any idea of efficiency, don't you have to worry that that software is maintainable? I mean, what are the software engineering concerns that you may also need? Otherwise, 5 years from now, you may have a little monster that all your wonderful collaborators across the globe, they just won't be able to put their hands on. So there's two things, so speak whatever you want about.
Okay, thank you. Yes, for the first thing, we did a little bit of it, which was involving people from, for example, underprivileged neighborhoods in the ideation, in having the ideas for the innovation. We directly didn't do, but we worked with NGOs that do work with those people. So, for example, we have this bike science project that is a data science to analyze the cycling trips. And what we did, there are a few non-governmental groups here in São Paulo that they are cycling activists, and they have a very large penetration in the let's say low-income neighborhoods of the city, because most of the cycling tracks are in the rich areas. There are very few cycling tracks in the periphery of the city where the poor live. And so we have worked with them to understand their needs and what would be the potential for cycling in those areas. And then we directed our analysis in that case to meet those requirements. That, okay, how can we make these cycling tracks reach this different neighborhoods that are not served now? So I think this is a very interesting thing to do. It's not in all of the projects that it's required and it makes sense. For example, when we are talking about health, I don't think it makes much sense for me and my team to go talk to the people that get the health service with the patients, because the doctors that are in our team, they have been doing that for 30 years and they do that in a daily basis. So I think I prefer to talk to the doctors that are in the front line than to talk to the real users. Well, our users are also the doctors. So yeah, sometimes it makes sense and it's great to do that, and sometimes not necessarily. Regarding maintainability, yes, it's a big problem we have. Right now, we are well-funded. We have a well-funded research project for three more years. We had 3 years in the past and 3 more years in the future, in which we can pay a small company just to do maintenance of our middleware. Because as we know, that when you use graduate students to develop the middleware, the graduate students, what they need to do is to build a proof of concept to get their thesis done, and then they are gone forever, and they don't want to see your face anymore sometimes. So you do need a team. Our team should be better, should be larger and more professional. If we had more resources, it would be nice. And I'm sure I can maintain it for 3 more years. To maintain it in the long term, we would need to build a large open source community around it, which is not easy at all to build such a community. But my guess is that if there's a city government that really wants to adopt it, then I will make it very clear. Okay, but there's this amount of this budget that you must reserve every year just for maintenance. Because if you leave a software alone, it breaks after a while with new libraries, new versions of languages being released every year. If you don't maintain it, it just dies after a while. So you must make that clear to the government official that there's that early budget that it's just to keep the system working without any new functionalities. Yep.
Very good. So we have, questions from Piap. So there is one from Nalini Venkata Subramanian. IoT sensors and connectivity often have reliability concerns. So are you considering techniques to ensure that your services are reliable in the presence of failures?
Yes. Well, right now, we don't have a middleware to support that, but some of our applications that are sensitive to this kind of failures, they have their components to do that. For example, that bus dashboard that I showed, it gets information from those 15,000 buses in real time, twice per minute. Every 30 seconds, you have the location of 15,000 buses. But some of the locations come completely wrong because the GPS fails. Sometimes a bus is running in Rio de Janeiro or in the middle of the Atlantic Ocean. So we do have some machine learning components there just to do a data cleaning, for example. And if you have any, and this is not like safety critical application, because in the worst case, you have the wrong color in the map or something like that. But if you are controlling something more serious, like power plant, then you need even more components to make sure that your data is sanitized before you take strong actuation commands. Because yes, the sensor data is a large percentage of it is wrong and sometimes very wrong. And it's not just that you don't have the data comes very wrong. So you need to take care of that. Very good.
Paulo Ferreira also has a question. So can you provide more details regarding your initiatives? You have a master's or Smart City or anything similar for the teaching of some of such ideas and that comprise the cross fields you did. So yes, what is your educational model? That's a great question, Paulo. Thank you.
Yeah, okay. Yeah, we don't have a specific bachelor's on that. We work within the bachelor's of computer science, and we have a few bachelor's and master's and PhD and postdoc in computer science. And we have a few courses that are very practical courses in which the students learn by doing over the semester. So as Martin said in his keynote, I don't believe anymore in a lot of lectures and textbooks. For a long time, I have been doing these practical courses. So we have, like, for example, one that's called Agile Software Development, in which we bring external customers to bring their problems. We have another course that's called Smart City Application Development, in which we bring researchers that think about the city to propose together with the students, innovative applications, and they develop over the semester that application. And we have a data science laboratory in which we get external customers that normally are researchers from other fields, health, mobility, engineering, economics, and they bring their research questions, and our students need to interact with them, learn to talk to people from other areas, which is very difficult for them at first. And then over the semester, using an agile method, they develop the solutions. And some of them are so good that we incorporate as a major thing in our project. Some of them become research papers. Some of them, a few of them are in the end transferred to, in our case, transferred to city government. We had a couple of cases in which that happened.
Nalini has a second question. Security and privacy. So, what are the concerns that govern capturing the data from the communities, how you face those concerns in your project? And I will tag on and also ask about any bias in the data, any ethical concerns more in general that you want to talk about for this kind of project.
Okay. Yes, security and privacy. Privacy first. Some of the we deal with data from health of the patient, real people. So we have real data, detailed data about the health of real people. And I'm very afraid of bringing this data to the university. So the thing we do, we work together with the government officials to anonymize the data. They already have their protocols, but we also help them in improving this anonymization there at the Secretary of the Government before bringing the data to the university. And so when the data gets to the university, in the notebooks of my students, I prefer to have that data as much as anonymized as possible. In addition to that, we have to have some protocols. We sign agreement with the student that the student agrees that he won't distribute this data to anyone else, won't publish on the web. So it's a big concern that we must take care. In mobility, there's also this problem because, for example, in this application here, we had automatic vehicle identification. We had the correct information of certain vehicles where in the state of São Paulo, where they were exactly in each moment. And more than that, the government wanted to know the mobility flows in the city. So we had to track the millions of cars moving in the state to build these flows. So again, we need to take a lot of care to when the data is not anonymized. Well, we don't have the name of the person, but we have the license plate to treat it as a very confidential thing. And only when we aggregate and we have the flows with thousands of cars, and then we can publicize and make it available. And the flows we can distribute to anyone, but the individual data we cannot. So this is a constant concern that we must have. I wish we had more research on privacy. We don't have yet. We have funding to support a postdoc in privacy, but we don't have the person yet. If someone listening to me now is interested in working with us, we have the funding. Thank you, Nalini. You are muted, Dilma.
Yeah, I'm trying. My cat is meowing a lot, so I'm trying to spare you guys. So Wei Wang is asking if you use right now edge computing infrastructure, and if so, what experience you had, technical challenges, and if not, what do you see as the potential for edge computing in realizing your vision for smart cities?
I think edge computing will be important, will have a role. Personally, my research group in São Paulo is not dealing with that, but this here. Marcos Andrew and Francisco Silva, they are developing middleware specifically for fog computing and edge computing. So this is very interesting work. I don't know in detail, but I would forward you to talk to them if you want. Write me and I will introduce you to him and he will work. I think not everything will make sense to run on the edge and the fog, because the cloud is something very powerful, and having a global knowledge that you can only have in the cloud it's very powerful for optimizations, etc. Just optimizing locally, it doesn't mean that you are doing a good well optimizing globally. So it's not for everything, but there are a few specific cases in which the lower latency that you have and also saving bandwidth can be a good option for you.
Very good. We do have to move on to the next part. We have a couple of wonderful questions. So one from Golden Blair about that he, contrasting with his experience building systems for rural environments, and another from Yogesh Barv.
I can answer later in the Slack channel.
If I will put them on the Slack, and all of us are very interested in hearing that.
Great, thank you.
So I'll copy it and we'll continue there. Thank you so much. Thank you so much. It was a great talk, and we really look forward to hearing more about you and all your collaborators. Hopefully they'll have papers on middleware also for us to learn more about it, okay?
Hopefully, yeah. Thank you very much, Dilma.
Okay, so Nalini, please.